Hello and welcome to today's lesson. In this tutorial, we will find limits of summation formulas. We are in the second part of our final topic in pre-calculus, part B, limits of summations. So we have 6 summation formulas that I'd like for you to get familiar with and to, of course, memorize. Let's please memorize these 6 formulas. It'll be pretty easy to memorize them as we use them and keep writing them. So let's do that and let's practice with them. Let me show you what they are equal to. Each one of them, of course, has a sigma where k equals 1 and goes all the way to n. So this first one is the summation of just a simple constant. This is just a constant like a 5 or a 7. And really then it just means we just need to know how many we have, and that would be this top number. So hopefully it makes sense to you that this would simply be the constant times however many there are, c times n. Not too difficult of a formula. Number 2, now k is what we're trying to add up, and k is our variable, which goes from 1 to 2 to 3 to 4 to 5, so we're adding up different terms. This will be equal to n times the quantity n plus 1 over 2. And I like to think of this as the arithmetic sum formula, and actually it is. The number of terms divided by 2 times the first term plus the last term. So if that helps you to memorize this formula, that would be great. Number 3, we're adding up perfect squares. 1 squared plus 2 squared plus 3 squared plus 4 squared, all the way to however many squares we have, will be n times the quantity n plus 1 times the quantity 2n plus 1 all over 6. A little bit more complicated of a formula, but we'll be using that a bunch of times, so you'll get familiar with it. Number 4, we're adding up a bunch of cubes. 1 cubed plus 2 cubed plus 3 cubed. This is equal to n squared times the quantity n plus 1 squared divided by 4. Number 5, we have a summation of either a sum or a difference of two things. And what we can do with that is we can take each summation individually. We can take the summation of a sub k and then add or subtract the summation of b sub k. So basically, if we have the summation of a sum or a difference, that's equal to the sum or difference of the individual summations. So that's an important property, and we'll be using that in our practice. And finally, formula number 6, we have a constant times something. And if we have that situation, we can take the constant out and say that that's equal to the constant times the summation of a sub k. Any constants that you have in here we can pull out, sort of like a GCF, I guess, and then have our summation by itself. So these are the 6 summation formulas. We'll memorize these. I'm going to refer to them by number in our notes today. Before we get into our example 2, I'd like to look more in depth at this formula number 3, the sum of a bunch of squares. In example 1, I'd like to evaluate this. This is adding up the first 17 perfect squares. And instead of listing them, 1 plus 4 plus 9 plus 16, I would like to use the formula that I just showed you. And that formula says take however many perfect squares you're trying to add up and put that right here for the n, or right here for the n, and right here for the n. In this case, our n is 17. So this should be equal to 17 times 17 plus 1 times 2 times 17 plus 1 divided by 6. And if I might simplify that before I plug it into the calculator, that would be 17 times 18 times 2 times 17 plus 1 is 35 divided by 6. 17 times 18 times 35 divided by 6 is 1,785. So that's just using one of the formulas and plugging in a value of n into it to get the number much more efficiently than a brute force method. Okay, but now let's look at some of the examples that were looking forward to in this topic. Example number 2. It says to evaluate this summation for various values of n. I'm not very interested in these right now. We'll do that in a bit. What I'd like to do is rewrite this. I need to work with this until it becomes something that is efficient to plug an n in. I don't really want to plug an n right now because k is just a number that keeps changing. K is my variable. K goes from 1 to 2 to 3 to 4 to 5 all the way up to whatever n is. I understand that n is a letter, but in this case, n is representing a constant, and it's important for you to note that. N is a constant. If n is 50, then n will be 50. K will grow from 1 all the way to 50. K is my variable, n is my constant. So I see formula number 6 in play right now. I see there's a 1, I'm going to put parentheses around the k plus 2. I see a 1 divided by n squared, and I can take that as a constant out using formula number 6. So 1 over n squared being a constant, I can pull out and have the summation of, I'll keep the k plus 2 in parentheses, and that's what I have now. I pulled my constant out using formula number 6. And now I see that I've got this sum right here. And I can use formula number 5 to split it up. Now I've got my constant out here. It's going to be the first thing I write. And since I'm going to split this up, I'm going to use parentheses. I'm going to have the sum of the k plus the sum of the 2. That's using formula number 5. And now I see I have this, and I know what formula that's going to be equal to. And I have this, and I know what formula that's going to be equal to. I'm going to be using formula number 2 for this one, and I'm going to be using formula number 1 for this one. So let's do that. I'm trying to color code here, so everything that's in red is not changing. I'll do that. How about that? Formula number 2 says I can take this, where the k is right here, and say that that's n times n plus 1 divided by 2. And formula number 1 says if I have a constant here, I just multiply the constant times n, and I've got 2n. So what's happened now is my sigma notations are all gone, and therefore my k is all gone. All I have left is n. So this is a whole lot more efficient that I could plug an n into this. Now I can simplify this more, and I'd like to do that, make it even more efficient. I'm going to leave this 1 over n squared out for a little bit. And let's see what I have here. I've got two fractions trying to become 1, so I'm going to put this over 1. I need that common denominator of a 2, so I'll multiply by 2 over 2. And let's see what we have. I'm going to be able to put this all together as one big fraction. I'll do the n squared plus n. That's just distributing. Plus, this becomes 4n. And since it's all over 2, it's all over 2. And now I can, well, I guess I have some like terms here. That'll make 5n. So this is 1 over n squared. And this is n squared plus 5n divided by 2. Next, I can multiply straight across here. So 1 times the numerator, of course, is just the numerator, n squared plus 5n. And n squared times 2 becomes 2n squared. Pretty good, although now I see that there's an n in every spot, so I can actually reduce that. N plus 5 divided by 2. N. 2n. Okay. So this is an expression that is equivalent to our original summation. And this is something that's a whole lot easier to plug an n in. So now I'm interested in what's behind my box, right there. Let's start by plugging in 10. If n is 10, then my summation will be 10 plus 5 divided by 2 times 10, which is 15 over 20, which would reduce to 3/4. Okay? Let's make n 100. If n is 100, I have 105 divided by 200, and that would reduce to 21/40. Let's keep increasing n. Let's say that n is 1000. If n is 1000, then this is 1005 divided by 2000, and that would reduce to 201 divided by 400. Let's keep going. Let's make n 10,000. If n is 10,000, 10,005 divided by 20,000, that would reduce to 2001 divided by 4,000. So what's happening to the, well, not really so much here because this is such a tiny value of n, but as n is getting larger and larger and larger, what's happening to my sum? Or rather, if n were infinity, what would my sum be equal to? Well, that means that I would need to take this expression and find the limit as n approaches infinity of it, n plus 5 divided by 2n. And this is a limit of infinity, just like we looked at in our last tutorial. Because the degrees are the same, they're both 1s, this plus 5 is not really doing anything, then we know that we've got our leading coefficient, and it does look like these fractions are trying to become 1/2, and that's why this limit is ultimately 1/2. So today we're going to be looking at limits at infinity, limits of summation formulas, and this is our process. We're going to be given a summation. We need to use our properties, whatever properties they are, to substitute and rewrite algebraically into an expression, and then ultimately we're going to be finding the limit as n approaches infinity of that expression. That's example 2. Let's look at example 3. Example 3 says find the limit of s of n, here it is, as n approaches infinity. Well, like we did in the last problem, let's deal with this in the end. We'll talk about n in a bit. We need to work with this until we can get something that's efficient to take the limit. Our goal in this problem is to be able to take the limit of this thing. And ultimately, I need to get rid of this variable, this k. Okay, so let's start by, I see this constant. Remember, n is a constant, so this 1 over n, I'm going to be using number 6 and pulling this 1 over n whoop, right out here. So I've got 1 over n, and then I've got everything else. The summation of, I've got a 1 plus a k over n quantity squared. The next thing I see I should probably do is FOIL this binomial. I'm actually going to come off to the side here. 1 plus k over n times 1 plus k over n. Let's FOIL that real fast. First terms give me 1. Outer terms give me a k over n. Inner terms give me another k over n. Last terms give me k squared over n squared. These are like terms, giving me 2k over n. And I FOILed it. So now I've got 1 over n and my sigma, and I've got my 1, my 2k over n, and my k squared over n squared. It was important for me to have these as individual pieces so that I can use my formula number 5 and separate my sigmas. So I've got 1 over n, and then I'm going to have 3 separate sigmas. It's not really distributing, but you can sort of think of it like that. So I've got the sigma of the first piece, 1, plus the sigma of the second piece, 2k over n, plus the sigma of the third piece, k squared over n squared. What I see next is another constant right in this sigma and another constant right in this sigma. So I'm going to be using property number 6 in both of these. So let's see what we've got now. I know I can substitute for this. I'm not going to do that yet. I'm going to substitute all at the same time. So I'll leave that alone. I'm going to pull the 1 over n out of just this individual sigma, and I'm left with 2k. Ooh, I should have pulled out a 2 over n. Yeah, let's do that. Whoa. Yikes. We'll pull out a 2 over n. This whole constant will come right on out, and I'll just have my k. Move that over. Plus, I see a 1 over n squared, and I'm going to pull that out just out of this individual sigma, and I'm left with k squared. Okay, now it's time to substitute. This is formula number 1. This is formula number 2. This is formula number 3. Let's see what we've got. We got this 1 over n. Formula number 1 says just the constant times n, so that's 1 times n. I'll just put n. I do have this 2 over n. Formula number 2 says we've got n times n plus 1 divided by 2. Don't forget the 2 over n here. And I've got a 1 over n squared here. Formula number 3 is the n times the quantity n plus 1 times the quantity 2n plus 1, all divided by 6. Close that parenthesis and close that parenthesis. So I am running out of room here. I'm going to move on to the next page, and here it is, rewritten. So I did get rid of all of my sigma notations, so therefore there are no variables left. The k is all gone. This is all just n. But what I really need to do is make sure that these are individual terms, because I need to take the limit as n approaches infinity. So I'm going to clean up some of this stuff. Let's see. I see in this term an n can cancel away. I know that the 2 can cancel away, so that's not too bad. I know one of the n factors from the numerator can cancel with one of the n factors in the denominator. Let's see what I have here. I'm going to leave the 1 over n for just one more. I've got the n. This is just, well, n plus 1, so that's nice. These are all separate terms. I do have this 1 over n times this. So 1 times all this, I'll just FOIL this, and that's going to be 2n squared. N outside, 2n inside, that's 3n. And my last terms are 1, all divided by 6n. And I'll close that parenthesis. Okay, that's not too bad. And I'm just going to distribute this 1 over n into that term, and that term, and that term, and that term. That's not too bad. So 1 over n times n is 1, and 1 over n times n again is 1, and 1 over n times 1 is 1 over n, and 1 over n times this, well, 1 times the numerator is not going to change it, and n times the denominator makes this 6n squared. Oops, I guess I didn't really have parentheses there. Let me get rid of that one. So this is okay. I know I could get more common denominators and get it all to be one fraction like I did in example 2, but example 2 had a different goal. Example 2, I wanted to plug values of n in. This time, I really just want to take the limit of this as n approaches infinity. And that's what I'm going to do right now. The limit as n approaches infinity of 1 plus 1 plus 1 over n plus 2n squared plus 3n plus 1 over 6n squared. So I like that I have 4 separate terms, 1, 2, 3, 4, because I can take the limit individually of each of those terms. Now remember, this is the limit as n approaches infinity. As n approaches infinity, 1, well, 1's going to stay 1. And this one is going to stay 1. The limit as n approaches infinity of 1 over n becomes 0. We learned that in the last tutorial. And the limit as n approaches infinity of this fraction, because the degrees are the same, the leading coefficient will be what it's equal to, 2/6. That's actually 1/3. So we've got 1 plus 1 plus 1/3. I might think of this as 3/3 plus 3/3 plus 1/3, and I can see my final answer is 7/3. Whew, love it. What a fantastic problem that is. A lot of good work. Go back and watch this if you need to. We'll practice this in class, and we'll practice substituting those formulas. I do have 2 try problems. I'd like for you to, pause the video, work on these. I will fill out the answers and you can see, but I'd like for you to try 1 and try 2 for class. Pause the video now and see how you can do on try 1. Thanks for trying this. Here's a little bit of try 1 just to get you started. Why don't you check if this is all accurate on your page? When you are ultimately done, I want you to take the limit as n approaches infinity of your final answer and see what the limit is. All right, pause again and continue. Thanks. Here is the remainder of try 1. Your expression might look different. You might have gone a little bit farther. That's fine. Ultimately, your limit as n approaches infinity will be 1. Thanks for trying try 1, and here is lovely try 2. I'm going to work a little bit of it while you work a little bit of it. Please pause. Okay, thanks for trying this. I got it as far as getting rid of all of the sigmas, or both of the sigma notations that I have, and this is where I am right now. The next job is to use some algebra skills and clean it up until they're individual terms. Pause and continue. All right, and here is the problem complete. My final expression looked like this. You might have gotten common denominators, and maybe it looked a little bit different. That's fine, as long as the limit as n approaches infinity of your expression is equal to 2/3. That is our final answer. Thanks for paying attention in this tutorial. We will practice this in class. Please bring your questions with you. Thanks for watching. All right, see ya.